Good morning, friends. I'm just curious to know how was the quiz like? So maybe could you raise your hand if you think you got the idea of the first problem in the quiz? Yeah, the Facebook problem. Okay, how do I count the number of hands? Okay, ठीक है, 24 out of 59. Oh wait, it's much more. Okay. So roughly half the class got it. Okay, I'm happy. What about the second problem? So raise your hand if you think you got the second problem, at least the idea. I mean, you got the second problem, the idea of the second problem in the exam, not after the exam, during the exam. Okay. So, okay, not as many people. Okay, fine, sounds okay. All right. Um, okay, what is the plan for today? Or rather, what is the plan for the remainder of the course? Yeah, you can lower your hands now. So the plan for the remainder of the course is to study some extremely abstract mathematical structures which essentially capture the so-called what should I say, nice properties or extremely high-level, easy-looking properties that we have seen so far, right? And just keep this statement at the back of your mind, and we will keep on visiting this statement again and again during the remainder of the course. Okay, Sachit, your hand is up.
Sorry, sir, I forgot to lower it.
Okay, no issues. Okay, so recently it so happened that the head of our department, asked us to fill up our preferences on what courses we want to teach in the upcoming semester, right? So we were supposed to fill up a form where we indicate, right? So what course we are willing to teach and in which slot. Okay, so let me just present to motivate the notion of a relation. Let me just present a small subset of that data over here, right? So the set of faculty contains several people. So these are probably the people whom you know: Amitava, Venkata, myself, Vireshwar, Adi, and so on. There is a lot. There is a big set of courses that the computer science department runs. So maybe these are the courses which you are familiar with, and then every course runs in several one of several slots, right? And so this is the kind of data we obtained, right, out of um, as a result of people filling up the form, right? So Amitabha is willing to teach 202 in slot B and so on, right? So mathematically, right? So if we consider these three sets, what is this mathematically? What is all this mathematically, right? So this is just some, oops, this is just some subset of F cross C cross S, right? So this whole thing, whatever we have over here, is just some subset of F cross C cross S. Okay, and this is what we call a relation. Okay, so informally, right? So this is just a motivating example. So informally, this is what is called a relation. So also known as a relation. Okay, we'll define this formally, of course. Um, okay, yeah. Um, so next year you might be doing a course on databases, right? I'm not sure whether it's a core course, whether all of you are supposed to do it. I'll have to find out. But some of you, at least some of you, might do it, right? And then that is where you'll study something called a relational database. Okay, and this is exactly the kind of data you will deal with when you study relational database. Okay, so it will consist of several tables, and each table is really a mathematically it's a relation over a couple of sets. Okay, so let's put this down mathematically. Okay, we'll draw the line. Okay, so mathematically, a relation are on a tuple of sets right? So we are looking at a tuple of sets, not a collection of sets. Let's call the sets, let's say S1 through Sk is nothing but a subset of the Cartesian product of these sets. That's it. Mathematically, it's nothing more than that. Okay, so what you can see over here is, yeah, obviously relation. So let me add something to this definition over here. Okay, a k-array relation. Okay, where this k really refers to the number of sets whose product we are considering over here. Okay, and moreover, so the number k is called the, so the definition of relation, this number k is called the arity of R, right? So arity just tells how many sets are really involved in the relation, right? So what you can see over here on the left hand side is a three-array relation, also known as a ternary relation, and obviously its arity is 3. Okay, so yeah, I mean, it's customary to call a three-array relation a ternary relation, two-array relation a binary relation, one-array relation, which is just a subset of the single set you are looking at, right? So it's customary to call it a unary relation, if you will. Okay, so remember, right? So note, right? What is a relation after all? It's just a subset of this Cartesian product. So therefore, if R1 and R2 are relations, okay, I should say a relation R. Okay, no, I have written it properly. Relation R on a tuple of sets. Okay, so if R1, R2 are relations on a tuple of sets, let's say on the same tuple of sets, let's say A1, or rather S1 to Sk, then it makes sense to do all the set operations on them, right? So R1 union R2, R1 intersection R2, what else? R1 set minus R2, R1 complement, etc. are all relations on S1 through Sk. Okay. So nothing too much interesting happening over here, but when we will start imposing conditions on the kind of relations we are looking at, several nice things will come up. Okay, so any question before we do that? Okay, no question. Cool. Okay, so now our focus for the next few classes is going to be on binary relations only. We will not, I mean, we will hardly look at ternary or four-array or five-array relations and so on. Our focus will be
Sir,
primarily, yeah.
sir, why you skip the G slot in the set of slots?
Well, that's not a slot if you look at the IITD timetable. That's all.
Yes, sir. Okay.
Okay. Yeah, nothing specific about it. I just tried to make the data as much real as possible. That's all. That's the only explanation. Okay. Yeah, so our focus is going to be on binary relations, and moreover, binary relations on a single set. What do I mean by that? So binary relation on a tuple of two sets, both of which are the same. Okay. So our focus will be on binary relations, or let me put it this way, two-array relations also known as binary relations on a given set S. And what does that mean? That is on the tuple of sets S comma S. right? So basically, you're looking at any subset of S Cartesian product S. That's all. Okay. And whenever you're looking at a binary relation, might not be over the same set. It's customary to write it in a slightly different way. So instead of so if R is binary, R is a binary relation. Right. So we also write. Right. So we also write something like xy in R. Right. So this can be also written as x r y. That's all. Right. And why have I introduced this kind of a notation? That will be clear when we look at concrete relations. Right. Or let me just give the answer away. Right. So if you just look at the equality relation on the set of integers, let's say. Right. So you never write 5, 5 belongs to the set equal to. What do you write? You just write 5, 5 is equal to 5. Right. If you look at the less than or equal to relation, right? So it's what is a less than or equal to the less than or equal to relation? After all, it's some very specific subset of z cross z, right? Less than or equal to relation on the set of integers is just some very specific subset of z cross z. That's all. Okay, but you never write -3 comma -2 belongs to the relation less than or equal to, right? So you never write, although it's mathematically it's okay to write that. Let's say -3 -2 belongs to the relation less than or equal to, but what do you usually write? -3 is less than or equal to -2, right? So which is why I introduced this notation. Okay. Any questions so far?
So the binary relations are defined that both the sets have to be same.
No. That's not. No. Binary relation is just a two-ary relation.
Okay, sir.
Okay, so it's a relation on just a subset of some A cross B, that A and B are two sets. But our focus is going to be on binary relations where these two sets A and B are the same. Okay, and that will give us some more nice properties to study.
Sir, R can be a null set also, no?
Maybe what?
Sir, R can be null also, right?
R, yes, potentially R can be null, right? So then what are all possible? How many relations on the empty set do you have? How many binary relations on the empty set do you have?
Sir, one.
One. Why? So binary, okay, empty set. So basically empty set cross empty set is just the empty set. And now you are looking at subsets of the empty set. So yeah, you just have one relation. That's true.
Okay.
That's true, which is the empty relation. Yeah. So by the way, I should have mentioned over here. So the, right. So let me just shift this a bit. Good that you reminded me. I should have mentioned over here that the empty set and so these are the kind of extreme cases. Empty set and S1 cross S2 cross Sk are also relations on the same tuple of sets S1 through Sk. Okay, so you could very well have the case that people are so much fed up with teaching that everybody says, no, I don't want to teach any course in the next semester. Okay, which is practically impossible, but theoretically, yes, it's possible. Okay, fine. So let's move on. Okay, so now for the next few minutes, let's put aside this notion of relations and let's consider the following situation. Okay, so let's say cousin of yours visits you. Okay, so she is a, let's say, 10-year-old girl, and she asks you, Bhaiya, Didi, Could you tell me what is a rational number? I mean, in school we have studied the notion of integers. We know I know what are integers. I know how to add integers, subtract integers, multiply integers, test whether an integer is divisible by another integer, right? And in that case, I know how what do you mean by dividing integers. But what is this rational numbers business? Could you just explain it to me? Okay. How would you explain it to them? Any volunteers for doing that? Manthan, yes.
A rational number can be said as a relation between P and Q.
So so she doesn't know what is a relation. So let's not bring relations over here,
Okay,
right? So your cousin just knows what is an integer.
He knows the subset, na? Cross notation.
Okay. Let's say they know the Cartesian product. Okay, fine.
So a rational number can be defined as a P cross Q, where P and Q both belongs to the integer sets, such that P and Q both are co-prime.
P and Q both are co-prime. Okay.
A rational number P by Q can be represented. A rational number.
Yeah. So what you're saying is a number of the form P by Q, where P and Q are integers, and GCD of PQ is equal to 1, right? So this is what you mean by a rational number.
And so basically, rational number will belong to P cross Q, no? Every rational number can
be. So basically, you're saying the same thing. You're saying that this P comma Q tuple belongs to Z cross Z. Okay.
Yes.
This is what you meant. Okay. Yeah. So you said the same thing.
No, sir. It should belong to Z cross N.
Sorry.
It should belong to Z cross N.
Z cross N.
Yes, sir. Who is a natural number?
Who is it? One sec. Who is this? Arin. So Arin says, well, this should change to Z cross N. Why did you say Arin?
No, GCD P by PQ equal to 1. So Q cannot be 0.
Arin, what is the answer?
P equal to 1, Q equal to 0. GCD is 1.
P equal to 1, Q equal to 0, and that's not a rational number. Cool.
Yeah.
Makes sense. And moreover, right? So something like -3 by -2 and 3 by 2, according to Manthan's definition, would be different rational numbers, but that's not the case. Right? Okay, cool. Right, but okay, I was not expecting this kind of answer. I was expecting something like, okay, mathematically rational number is nothing but so let me just put the naive way of defining rational numbers, and you'll have to decide whether it's a correct way of defining or rational numbers or whether it is wrong. Right? So what if I just say that, okay, rational number is nothing but a number which is written in the form P over Q, where this tuple PQ is just belongs to this Z cross Z. What is the problem with defining rational numbers in this way?
3 by 2 and 6 by 4 are different.
Yeah, so so that is, but more fundamental reason, the more fundamental problem is, yeah, what you said is the right problem. You have pointed out the right problem, but there is more fundamental problem over here.
0 by 0.
Yeah, so something by 0, not just 0 by 0. So yeah, Abhinav, okay, I get your point. Okay, yeah, so basically, so let's get rid of that problem by saying this Z minus 0. Right, and then the other problem pops up, right? So we don't want to say that 6 by 4, I mean, we don't want to treat 6 by 4 as a different rational number than -3 by -2, let's say. Okay, right? So how will you explain what is a rational number to your cousin? So you could say, okay, well, it's just a number which is written in the form P over Q, where PQ is a tuple in Z cross Z minus 0, but we treat, right? So we treat a rational number A over B the same as C over D whenever, right? So we treat them as equal whenever what? Divyanshu?
Sorry, sir, there was some problem. Like, I don't know I'm unable to lower my hand.
Okay, no issues. Okay. Yeah, whenever what? When do you treat A over B equal to C over D? People are replying or chat apparently. Yeah, yes, Abhinav, you are right. Shrimanti, you are right. A times D is equal to B times C. Right? So what you're doing essentially over here is the following. So you're looking at this Cartesian product of these two sets, Z minus Z cross 0. I'm bad at drawing good diagrams. Okay. So this is my set. Z cross Z minus 0. Right? So firstly here I am defining some kind of a relation on Z cross Z minus 0. I am saying that AB, okay, let me put this as an equality because this is the equality of rational numbers, right? So mathematically what I'm doing is I'm saying that AB is, right? So AB represents the same rational number as CD if and only if AD is equal to BC, right? So my relation, right? So this relation that I'm talking about is the collection of all pairs of pairs AB, CD such that AD is equal to BC. Okay. So this is one way to look at rational numbers, and another way to look at rational numbers is the following, right? So what you're doing is the following. You're getting back to this set Z cross Z minus 0, and you're dividing it into several parts. How are you dividing the set into several parts? You will say that, okay, well, AB and CD belong to the same part if and only if AD is equal to BC. Okay. So, right, so AB and CD belong to the same part if and only if AD is equal to BC. Okay, and then from each part you just pick up one rational number as a representative. What rational number you pick up? So Manthan's choice was pick up one rational number where the ratio of the numerator, the GCD of the numerator and denominator is 1 and the GCD is and the denominator is positive. That was one possible choice of picking a representative from each part, and then you define that set of representatives to be the set of rational numbers, and then after that you define how do you add two rational numbers, how do you whatever, multiply, subtract, divide, and so on. Okay, so that is the way you mathematically construct the set of rational numbers from the set of integers. Okay, so why did I at all mention this? So let us focus on this relation. Okay, so the pair AB is related under that whatever, or let us read this relation as represents the same rational number as. Right, so AB represents the same rational number as CD if A times D is equal to B times C, if and only if. Right, so what nice properties does this, or trivial looking but yeah extremely crucial properties does this relation satisfy, right? So first of all, AB, I mean just by what this English phrase tells you, it means that, okay, well, AB should represent the same rational number as AB, right? That's a trivial looking property, right? So AB represents the same rational number as AB. Secondly, another trivial looking property, if AB represents the same rational number as CD, then CD represents the same rational number as AB. Extremely trivial property. Well, so just note that due to due to the understanding that we have about this relation, these become trivial properties. But in general, an arbitrary relation might not satisfy these kind of properties. Okay. Third property, the third trivial property that this relation satisfies is the following. So if AB represents the same rational number as CD and CD represents the same rational number as EF, then what? AB represents the same rational number as EF. Right, so this is what intuitively we would expect, but then if you define the relation in this manner, where is my pointer gone? Yeah, if you define this represents the same rational number as relation in this manner, this requires a little proof, right? So if you just blindly take this as your definition, right, a little bit of effort is required to prove this third statement. If AB and CD represent the same rational number and CD and EF represent the same rational number, then AB and EF represent the same rational number. So in other words, you are trying to prove that if AD is equal to BC and if CF is equal to DE, then AF must be equal to BE. Okay, fine. So yeah, so this is what, so a relation which satisfies these kind of three properties, this is the first, this is the second, this is the third, is something called an equivalence relation. Okay, so let us put down the definition. Okay, so actually I'm going to put down several definitions over here, right? So let R be a relation on a set S, that is R is some subset of S cross S. Okay, so we are going to define several properties of this relation R, and one of them is going to be the notion of an equivalence relation, right? So R is said to be let me begin the bullets here, reflexive if X is related to X, or rather, let me put the quantifiers first, right? So if for all X in S, X is related to itself under R, right? So that is what we had over here when we said that a rational number, pair AB represents the same rational number as the pair AB. Okay, it's called symmetric if for all XY in S, what do you have? X is related to Y if and only if Y is related to X. Okay, so in other words, or rather, yeah, note. Yeah, X. So I have put an if and only if over here, but then even if I put equivalently, I can just put a single-sided implication, right? Because there is a for all XY in S quantifier over sitting over here. Even if I put a single left to right implication, that really means the same thing. XRY implies YRX. Okay, and thirdly, this relation is said to be, or rather, let me change this to number. So this, let's call this 1, let's call this 2 prime. It's called antisymmetric right? So it's slightly opposite of being symmetric, not exactly. I mean, antisymmetric does not mean not symmetric, it's slightly different. So let me just put down the definition, right? So if for all XY in S, what do you have? x related to y and y related to x implies that x must be equal to y. Okay, so in other words, if x and y are different elements of S, right? So then either x is related to y or y is related to x, or nobody is related to the other guy. Okay, you cannot have a case where two different elements, right, are such that x is related to y and y is related to x. So so antisymmetric is something I wrote just because it's kind of immediate from the definition of what is symmetric. Although this relation that we have over here is not antisymmetric. Okay, and finally 3, a relation is said to be transitive if for all x, y, and z in S, right? So x related to y and y related to z implies x is related to z. Right, so if x is related to y, sorry, x is related to y and y is related to z, then x is related to z. So this, right, so what we had over here is, so this was just the reflexivity property. This is the symmetry, and this is the transitivity. Right, so another definition. R is said to be, I should have added this, let R be a relation on the set S, but I'm just keeping that. So R is said to be an equivalence relation if R is reflexive, symmetric, and transitive. Right, so why did I involve this notion of antisymmetricity over here? That will be clear in a couple of classes when we define something called a partial order, right? So partial relation will be called a partial order if it is reflexive, antisymmetric, and transitive. Okay, but yeah, let's postpone that to I don't know, lecture. Yeah.
Sir, if x is related to y but y is not related to x, then we will say right that it's antisymmetric.
Sorry, say that again.
Sir, if x is related to y but y is not related to x in that relation, then it's gonna be antisymmetric, right?
Well, so this should happen, right? So for every x and y, something like this should happen. For every x and y, right? At most one of x, y, and yx should belong to the relation R.
Okay, sir.
Right? So antisymmetricity does not refer to a specific pair xy. Antisymmetricity is, or antisymmetricness is really a property of the relation that you're talking about.
Okay, sir.
Okay. So, but yeah, let's not worry about antisymmetricity for now. Okay. Yeah, so let's just focus on equivalence relations for this class, right? So relation is said to be equivalence relation if it's reflexive, symmetric, transitive.
So in the case that we did before, S was a set of tuples itself, right?
S was a set of tuples. S was just a Cartesian product of Z with Z minus 0.
Yeah, okay, sir.
Okay. Okay, so far so good.
Excuse me, sir.
Yeah.
Sir, if some relation is not symmetric, then like if x r y exists, then y r x might not exist, right? In that case, it must be antisymmetric, right? Because the statement itself is false, so it has to be true for every x y.
Say that again.
Sir, if some relation is not symmetric, let's say, so
Not
if
symmetric,
x r y exists, then y r x does not exist, right?
Okay.
then in that case for every xy, xry and yrx is anyways false.
How
So
do
this
you
statement
negate the statement? Sorry, who is this?
Abhinav.
Abhinav. So how do you negate this statement? Right. So for all x and y in S, x ry implies y rx. What is the negation of
Oh,
this statement?
sorry, for some xy. Okay,
Yeah.
fine.
So if a relation is not symmetric, then it means that there exists some xy in S.
Yeah, got it.
Xy in S such that, oh yeah, let me just clarify it for the class. There exists some xy in S, so this right, so this symmetricity. Yeah, so what is the negation of that? There exists some xy in S such that x is related to y, but y is not related to x. Or let me, instead of introducing new notation, let me just say xy is in R, but yx is not in R. Right, so antisymmetricity differs here, right? So the quantifier still stays to be for all, and moreover, we allow, right? So we allow the obvious cases, right? So we allow an element to be related to itself. Okay, so we don't want to conflict with reflexivity when we define antisymmetricity. Right, but except for that, we don't allow two elements to be kind of related in both ways to between themselves. Okay. Right. So another way of viewing an equivalence relation is what we did over here, right? So instead of looking at this equivalence relation, right, represents the same rational number as, and then saying that okay, AB represents the same rational number as CD whenever AD is equal to BC. What was the other way we looked at it? We said that okay, let us classify the rational numbers on this basis, right? So let us put two rational numbers in the same. Let us partition this set Z cross Z minus 0 in such a way that two rational numbers, right? So two pairs are in the same part if and only if they represent the same rational number. Okay, so that is another way of thinking of a of an equivalence relation, right? So if I give you a set S and a partition of that set, well, I need to formally define what is a partition, but I hope you get the intuitive idea. If I give you a set S and I also give you a partition of that set S, that partition associated with that partition is a corresponding equivalence relation on the set, right? That is trivial, right? So you just say two elements are equivalent if they belong to the same part in the partition. Conversely, if you have an equivalence relation on the set S, that naturally induces a partition. So that is slightly non-trivial to prove. Okay. So what we are trying to establish in the next few minutes is the equivalence, or rather correspondence, between partitions of a set and equivalence relations on the set. Okay. But before that, maybe we should look at some more examples of equivalence relations, right? So let's do that. So examples, right? So one, well, so equality, right? So trivial example is the equality relation, right? So R is the set of all XX such that X belongs to S. Right, so we need reflexivity, so therefore such elements must belong to our relation. But if we just stop there, if that is the only set of pairs of elements in our relation, then that itself is an equivalence relation, right? So symmetricity is easy to verify over here. Transitivity, I mean, right, so x r y and y r z implies that x is same as y and y is same as z, so therefore x is same as z, right? So this is one trivial equivalence relation. Another trivial equivalence relation is the other extreme. What is the other extreme? What is the other extreme equivalence relation? Yeah. Right. So this is the smallest possible equivalence relation, right, on a given set S. Why? Because reflexivity forces you to add these elements to your equivalence relation, and as soon as you add them, the relation in fact becomes an equivalence relation. Right. So this is the smallest possible equivalence relation on a set. What is the largest possible equivalence relation?
So S cross S.
S cross S. Exactly. S cross S itself is an equivalence relation. Yes. So that is the other extreme. Okay. Fine. Right. So more non-trivial examples. What else? So let's say your S is the set of integers, and you fix some M, which is an integer, right? So you say R is the set of all xy such that x minus y is divisible by M. Or in other words, x and y are congruent modulo M. So the congruence modulo M is an equivalence relation on the set of integers.
Sir,
Yeah.
the antisymmetric relations that we have defined, so they are itself defined on the basis of an a relation equal to, right?
Which one? Antisymmetric.
Like we write that if for all xy belong to S, xry and yrx imply x equal to y. So that means that x and y belong to the equal to relation.
Yeah. So
like we need to have an equal to relation defined on the sets, right?
I mean that is kind of trivially defined, no? An element is equal to itself and the element is not equal to anything else in the set.
Okay.
Right. Okay. What else? Any other interesting examples? Right. So we have seen two very concrete examples earlier in this course. Which ones? Right. So just recall what all have we done in this course. We have seen two equivalence relations in kind of disguise. Obviously, I did not mention equivalence relations at that time because nobody knew what are equivalence relations. So, Amil, yes.
Two vertices u comma v being belonging to the relation if they are connected by a path.
Connected by a path. Awesome. So if G is equal to VE on the is a graph, then R is, let's say, equal to the set of UV such that UV is in R2 vertices in V and G has a path from U to V. Right, so we have seen that this is an equivalence relation. Well, here instead of a path, I could have also written a walk. Right? So every vertex has a zero length path to itself. If there is a path from U to V, then there is a path from V to U. You just reverse that path. And because there is an equivalence between existence of a path and a walk, that kind of helps us in proving transitivity. If there is a path from U to V and a path from V to W, that means there is a walk from U to V and a walk from V to W. Just append the two walks. That way you get a walk from U to W, and therefore there is a path from U to W. Right? So I hope you remember this proof. What else? We have seen one more. Yeah, Chinmay?
So like the cardinality relation on finite sets, like
Why
same cardinality.
Why finite? I mean, what you said is right, but why restrict to finite sets?
Like cardinality is defined. Okay, we can like in. I'm not
Right,
sure,
so-
but cardinality is defined in finite sets only, right?
Sorry?
cardinality is defined for finite sets only, right? Like,
no, but we defined the notion of when do two sets have the same cardinality? What did we say?
okay, injectivity, like bijection
Not
is a bijection.
bijectivity. Yeah. So if there is a bijective function between them, then we say that the two sets have the same cardinality. Okay.
Okay.
So let me just put it. So if so S is the power set of some or this is not the notation we use, no. So right. So S is some set, right? So R is the collection of all sets, all pairs of sets AB in 2 to the power S cross 2 to the power S, such that there exists a bijection between A and B. Right, so reflexivity is clear. The identity function is a bijection from between a set and itself. Symmetricity is clear. I mean, if there's a bijection, you can just invert it. What about transitivity? Transitivity is also obvious, right? How do you argue transitivity? Yeah, Ramanuj.
Sir, if there is a bijective function g from x to y and another function, so you can just take this of this and get another bijective function. So if you have g and f, then you can take g and
Yeah, so
g
G
of
is a
f
function
of.
from A to B, let's say, bijective. And H is a function from B to C, which is also bijective. Then what do you do?
H of g, or h of g of something, or g of
So
h of something.
H compose G, right? So G is going to take A to B and H is going to take, yeah, so basically H compose G is a function from A to C and it is also a bijection. Good. Any other interesting examples that you can think of?
So can we say that equals to relation is the only relation that is reflective, symmetric, anti-symmetric, as well as transitive?
Forget transitive. Equal to relation is the only relation which is reflexive, symmetric, and antisymmetric. You can definitely say that. You don't even need to add the condition of transitivity. Okay?
Which is implied by
which is implied by the other properties. Yeah, you're right. Okay. Any other? Yeah.
In equal to relation, why do we need to apply the condition for reflexivity?
Sorry.
So in equal to relation, why do we need to apply the condition for reflexivity?
Otherwise, you could just have an empty relation, right? That's not the equal to relation.
So empty relation would be symmetric.
Empty relation is symmetric, of course.
Yeah. Okay, sir.
Right? Just check the condition. Both sides are always false, no matter what x and y you take.
Yes. Okay, sir.
Right? So therefore, the if and only if part is true.
Okay, sir.
Yeah. So one more example that I would definitely like to mention is the following. Right. So 6. Let's say you have some function f going from some set A to B. Then R is the set of all xy in the set A cross A, right? So I'm defining a relation on the set A using a function f going from A to B. How am I defining that? So R is the set of all xy in A cross A such that f of x is equal to f of y. Right? So I hope it is easy to check that this is an equivalence relation. Okay. Okay, so as I mentioned earlier, there is a nice correspondence between equivalence relations on a set and and partitions of that set. So let us formally define the notion of a partition, although we have informally used this notion earlier. Let us put a formal definition in any case. So definition, right? Let S be a set, collection, let's say P of subsets of S is called a partition of S if the following properties are satisfied. First property, for all A in P, A is not empty. No set in the, the empty set does not belong to the partition. Or instead of saying that, I think the easier way is to say that the empty set, which is a subset of S, by the way, does not belong to this collection of the sets P. Second, right, the union over all A belonging to P of the set A, the union of all sets in P must be equal to S. Right, so basically what I'm saying is every element should be covered by some set. And thirdly, for all AB in P, if A is not equal to B, then in fact A and B must be disjoint. Right, so this is just I'm just formalizing the notion of breaking up a set into several small subsets. Right, so whenever you break a set, obviously you are not going to count these empty sets because they are just redundant. Right, so the union of all the pieces that you create out of a set is going to be the original set, and no two pieces are going to share an element. Okay, so what are the extreme, right? So if we look at examples, what are the extreme cases of partitions? What are the extreme cases of partitions?
So we take P as the whole set S.
P, well, so let us examine this mathematically, right? Let us closely examine this. P is equal to S. Is this a partition of S? Aniruddha? Aniruddha, your hand is up.
No, I had a different example, but
yeah, okay, I'll come to you then. So then, yeah, so this question is for everyone. If I just take P is equal to S, is that a partition of S? Is P a collection of subsets of S?
No, sir.
No. So how should I fix this quickly?
Like P equal to the set S. Like we have to put a set
Set
around it.
containing the set S. Yes. So that is a partition. So this is a partition. Right? What is the other extreme partition?
the set of all singletons of
Set of all singletons, yes. Right? So I can just write it as the set containing X such that X is an element of S. Right? And then you could have several other non-trivial partitions. Aniruddha, you had something to say, I suppose.
Yeah, that was my example.
Okay, cool. So now I'm not going to state the following result as a theorem. Let me just informally state it that right. So there is a nice correspondence between equivalence relations and partitions. On a set S, there is a nice correspondence between them and partitions of S. Right, so if I give you a partition of S, what is the natural equivalence relation associated with the partition? Well, X and X is related to Y if and only if X and Y belong to the same part in the partition. Right, so given a partition P, so given partition P of S, right, so it is naturally, or rather it naturally induces the following equivalence relation on S. So what is this equivalence relation? The set of all xy such that, right, what should I say? So there exists some A in P such that x and y are both in A. Right, so reflexivity is easy, symmetricity is easy, transitivity, how do you argue transitivity? There's one little, or this half statement, half sentence proof of this. How do you argue transitivity of this relation? Right, so remember, if P was some collection of subsets of S, not necessarily a partition, then this might not be an equivalence relation. I hope you can see this. How do I say that this relation is transitive? Why is that so? Rishabh, sorry, I didn't see your hand up probably earlier.
So you say if x and y are related and y and z are related. Now let A be the set in which x and y lie.
Okay. So when you say let A be the set in which x and y lie, you are using some property of the partition,
Yeah,
right?
I was going to prove that. Let A be the set in which both of them lie. Let it be some set. And if
Hold on. So when you say, there is a difference between saying let A be the set, let A be the set in which something happens, and let A be a set in which something happens.
yeah,
What is the difference?
we'll take A here. Then we'll prove that there's only one possible.
Okay. So why is there only one?
And now if there are two sets in which say y lies, then it will lie in their intersection, which is empty.
That's it. Right. So because the sets are disjoint, pairwise they're disjoint, right? So what does that imply? It implies that every element belongs to exactly one set. So basically the property number 2 and 3 and also 1 implies that for every element of the set S, there exists exactly one set in the partition which contains that particular element. Okay, and that is basically the proof, right? So there exists some, right? So let A be the set in which X lies, right? So you are also given that Y lies in A, and that will also imply that Z also lies in A if X and Y are related and Y and Z are related, right? So therefore X and Z lie in the same setting. Any questions? So this was a bit fast, I guess, but I hope you get the point. I mean, it's not so hard, I suppose. Any quick question on this? Okay, so now what about the other way, right? So given a partition, given an equivalence relation, R, does there exist a partition P which induces R? Right, so I'm asking the question in the other direction. Given an equivalence relation, can you actually construct a partition which induces the same equivalence relation? Any ideas? How should I construct this partition, if at all it is possible? No ideas? Yeah, Rishabh?
So for each element, let's define a set which is all the elements which are related to it.
Good, okay.
And now you just take all these sets, remove all the duplicate ones, and you get the part.
Very nice, very nice. Yes, Rishabh, you're right. You're right. Okay, so maybe I should have added this. Okay, Fine. So I'll do that. Better late than never. Okay. So let's answer this question on the next slide. Right. So let's define. Let's put a little definition over here. Let R be an equivalence relation on a set S for some x in the set S, this notation. So I'm putting x in square brackets and I'm putting a subscript R denotes the set. What set? So it is the set of all y in S which are related to x, such that x, y is in R, or in other words x, r, y. Right, and note that this is because this is an equivalence relation, because R is an equivalence relation, by symmetry what do you get? This set is also the same as the set of all y in S, such that yx is in R. Right, so this follows by symmetry. Okay, so now Rishabh said that the natural way of defining a partition associated with an equivalence relation is the following, right? So let's write it down as a theorem. Let R be an equivalence relation on a set S. Okay, so then what did Rishabh say? Rishabh said that okay, let us run over all elements x in S, and for each element let us record this set x sub R, the set of elements which are related to the element x. And obviously because we are putting them together, all these items together in a set, that implicitly means that we are removing the duplicates. Okay, so then this is a partition of S. Does somebody want to quickly tell the proof? Right, so let us maybe copy the definition of partition from the last slide over here. Yeah. Why is this a partition of S? Aniruddha?
So suppose by contradiction that it's not a partition of S, that is, there exist two subsets A and B such that their intersection is non-empty. Then that the element in that intersection is going to be equivalent to an element in A as well as an element in B. And then by transitivity, by transitivity, A and B, those two elements would lie in the same set. So that's why we obtain a contradiction, and it has
Yeah. So you told the most important part of the proof, which is proving this third property, right? So what you proved is if A intersection B is not empty, then A must be equal to B. The same as proving this. Right. But what about the other properties? Why is the empty set not in the partition? Well, every set in the partition is not empty because the set x sub R contains the element x, right? So therefore that is not empty. Union is A. Why? Because the element x belongs to the set x sub R, trivially, due to reflexivity. Okay, so right, so okay, let's do it this way. Let's make this into a proof. Right, so empty set does not belong to P because X belongs to the set XR. The union is S because what? Well, so right. So again, the reason is the same because X belongs to XR, and note that this follows due to reflexivity. Right, and then what about the third property? Right, so if right, so A and B, because okay, so then what happens? Okay, so what is the proof of the third property? The proof is as follows. So A is in P. Why is A in P? So there exists some X in S such that A is the equal A is the set XR, and then there exists some B. There exists some Y in S such that B is the set YR, and because A and B intersect, so there exists some Z in S such that Z belongs to A intersection B, right? So if A and B intersect. So what does that mean? It means that X are, so therefore X is related to Z and Z is related to Y. Why? Because Z, right? So X, right? So Z belongs to A, which is the set of all elements which are related to X. So therefore Z is related to X, and similarly Z is related to Y. So therefore X is related to Y. So therefore what? So Y belongs to the set A, and right. So use transit. So I'll let you complete this proof. Use transitivity to prove A is equal to B. Right. So here proof by contrapositive, and this is the proof by contrapositive. Okay, I wanted to make a couple of comments. What did I want to make? What comments did I want to make? Yeah, so sorry, I forgot to add this name over here. So X sub R denotes the set of elements which are related to X and is called and is called the equivalence class of X under R. Right? Chinmay, yes, I'll come to you. What did we just prove? We proved that if R is an equivalence relation, then its equivalence classes form a partition of the set on which the relation R is defined. Chinmay?
Sir, what was being said about duplicates? I didn't get that.
So basically, right, so what are you doing over here? You're going over all elements X in S, you're finding their equivalence class, and then you're putting that equivalence class into this set. Right, but then because this is a set after all, right, so this object, because this object is a set, it's not a multi-set, implicitly you're removing duplicates over there. Okay, that was just the point.
Okay, sir, got it.
Yeah. Okay, what other comment did I want to make? I'm just trying to recollect. Yeah. Okay. Cool. Right. So let us investigate a couple of questions. question. Let R and R1 and R2 be equivalence relations on the set S, on the same set S. What can you say about R1 union R2, R1 intersection R2? Are they necessarily equivalence relations? Right, so question is, or rather R1 intersection R2, R1 union R2 necessarily equivalence relations? Right, what is the grammatically correct way of saying this? Necessarily equivalence relations, or should I call it, should I write equivalence relations necessarily? I don't know what is a better way of doing it, but I hope you get the point. Right, so are these two necessarily equivalence relations? Any comment on that?
So R1 intersection R2 would be equivalence.
Okay, who is this? Ujjwal. Yes, so Ujjwal says that. So answer. Ujjwal says that R1 intersection R2 is necessarily an equivalence relation.
So R1 union R2 is not necessarily an equivalence relation.
Yeah, who is this? Arin, is it? Yeah, Arin, yes. And the other comment was Arin said that R1 union R2 is not necessarily an equivalence relation. Yeah, so Ujjwal, yes, why could you quickly tell what is the proof of the first claim?
Sir, if we for reflexivity we can say that if x comma x is in R1 and same x comma x is in R2, then it's gonna be in R1 intersection R2.
Yeah, so reflexivity is easy, yes.
So then for
all three are easy, right?
So sorry, sir.
All three properties, proving all three properties is kind of easy, right? For R1 intersection R2.
Yes.
Sounds okay. Let's not go too much into it. What about the union, Arin?
Yes, sir. So it would be reflexive and symmetric, but it would not be what? It would not be transitive. Let's just say A comma B is in R1, A comma B is in R1, and B comma C is in R2. Then A comma C does not necessarily belong to any of those relations.
Okay, so what?
So it won't necessarily belong to R1.
There's some background noise from you, I think. Okay, thanks. Yeah, so what Arin said is R1 union R2 is is necessarily reflexive and symmetric. Symmetric, yes, yeah, of course. Symmetric, yes, sure. Okay, but not necessarily transitive. Okay, cool. So this is nice. Fine. So now let us, since we have some time, 15 minutes, let us try to inspect this equivalence relation R1 intersection R2. Right. So we have just proved that there is a natural correspondence between equivalence relations on a set and partitions of that set. Right. So R1 is, let's say, associated with some partition P1. R2 is associated with some partition P2. What does the partition that is associated with R1 intersection R2 look like? Right. So R1 is associated with some partition P1, right? We know how to construct this, how to construct one from the other. R2 is associated with partition P2. R1 intersection R2, we know it is an equivalence relation, but what partition is it? What kind of, how does this partition look like? The partition which is associated with R1 intersection R2. Does it have some kind of a nice relationship with P1 and P2? Any ideas? Rishabh?
Is it the pairwise intersection of all sets in P1 and P2?
Correct. You're right. So this partition, and I think it's better if I leave for you to figure out this. So this is naturally associated with the partition of the form A intersection B, such that A is in P1 and B is in P2. Right? So run over every set in P1 and every set in P2, take their intersection. I should add something over here, right? And what? And what?
A intersection B is not empty.
A intersection B is not empty. Right? So you run over all sets in P1, you run over all sets in P2, take their intersection. If it is not empty, you include it over here. Okay. How many of you think this is kind of obvious and you will be able to prove this on your own? Raise your hand. I mean, in any case, I think I'll just give this as a tutorial problem, let you try out and discuss in the tutorial at an appropriate point of time. Okay, so that is a decent number. How many are these? So 10 out of 68. See, I think that, okay, immediately think that they can do this. So that's good. So I'll let everybody think on this. Okay, right. So now how much time do we have? 12 minutes. Fine, that's good enough for me to finish whatever I had planned. Right, so the next question I'm going to ask is the following. Right. So let's say I give you a set S and I give you some relation R on the set S. Okay. Right. So I want you to construct an equivalence relation which is a superset of R. So let me just write this down. Write down my requirements. So given set S relation R on S. Note that this is not necessarily equivalence relation. Want an equivalence relation let's call it R star, which is a superset of R. Well, there could be several equivalence relations that are supersets of R. One of them being, what is the obvious equivalence relation which is a superset of a given relation R?
S cross S.
S cross S, right? So that's not interesting. We want the smallest, in some sense, the smallest possible equivalence relation that is a superset of R. We want as tight an approximation of R by an equivalence relation. Right, so this is just an informal notion of approximation. I'm not going to formalize this, but I hope you just get the idea. Okay, so of the smallest possible size, or rather, let me not even call smallest possible size. Let me just put it as the smallest equivalence relation R star, which is a superset of R. Okay, so you should definitely immediately ask the question, what do I exactly mean by smallest? And then probably my answer would be that, okay, I say a set is smaller than other set if the first set is a small subset of the other set. But then your immediate concern should be, well, what if there are two relations? What if there are two relations R1, R2, which are both equivalence relations, and R1 and R2 are both supersets of R, but neither of them is a subset of the other. R1 is not a subset of R2, R2 is not a subset of R1. What is the relation that I'm looking for? So what is, I mean, based on whatever we have seen so far, this is more like an informal question. Given a relation R on S, if I want to kind of approximate it by an equivalence relation, which is a superset of R, what should I look for really? Right. So if I just say I want a inclusion-wise minimal relation, well, there could be several inclusion-wise minimal relations which are supersets of R potentially, right? Or is it not the case?
With the minimum cardinality.
Minimum cardinality, again, the same issue could arise, right? So I could have two relations R1, R2 of the same cardinality and which are both supersets of R. Is that possible? Somil?
So I think like while two equivalence relations might not always be comparable, but there will exist a smallest equivalence relation in the form that any other equivalence relation that contains R will also have to contain R star. Like
correct.
That would
absolutely. Very nice, Somil. Ramanuj?
Yes, sir. So we can also construct that relationship with, I think, it's like construction with some specific steps, I think. Like, but will it be possible to?
You mean algorithmically?
Yeah, algorithmically, I think it will be like pretty simple though.
You think it should be possible? Okay, fine, good. So one thing I should have done is right. So let me just shift this. So I should have. So in fact, I should have said let us not restrict to the intersection of two relations. In fact, and I leave this for you to check. In fact, if some let's call this set script R is any set of, right, it could be countable, uncountable, I don't care. It is any set of equivalence relations on S, right? So then, right, so every okay, R is a set of relations, script R is a set of relations, equivalence relations on the set S, and it might not necessarily contain all possible equivalence relations on the set S. It's some subset of the equivalence relations. So then is any set of equivalence relations on the set S, then the intersection of R, where this R belongs to the set script R, is also an equivalence relation.
Sir, can we prove this for uncountable? So for countable, you can do it. For uncountable.
Yeah. So even if script R is uncountable or whatever, I don't care. I can still prove this statement, and that just follows. I mean, the proof is exactly same as this proof of this statement. Right, I am not using, by the way, I cannot use induction in this case.
Yeah, that's why I was.
Induction will only let you prove that the intersection of a finite number of equivalence relations is an equivalence relation. So induction is useless for proving this kind of a statement. But I claim that exactly the same arguments which you use to prove that R1 intersection R2 is an equivalence relation, same arguments will give you that this object is also an equivalence relation.
Okay.
Right. So basically, XX belongs to each R in the collection script R. So therefore, XX belongs to every XX belongs to this relation, and so on. You just go on writing the proof. Okay. So maybe I'll as an exercise, I'll just add this to the tutorial. So let me inform.
This minimal relation is going to be unique or not?
So this is going to be the minimal relation. That's the claim.
So basically, we are just taking intersection of the minimum if it's not the subset of some bigger relation.
We are taking the intersection of all possible. Okay, so in this, if you come back to this question, you consider the set of all possible equivalence relations that are supersets of R. and then take their intersection.
And that's gonna be a relation, which is a
That's going to be an equivalence relation. That's going to be a superset of R. And moreover, every equivalence relation that is a superset of R is also going to be a superset of that relation.
Okay, sir.
Right, Chinmay?
So here R star can be R also.
What if R is not an equivalence relation?
Okay, we had a
right. So if R itself is an equivalence relation, then R star will be R. That is clear.
Okay.
Right? So okay. So claim let R be the set of all equivalence relations on S that are supersets of the relation R. So then so let R star be equal to the intersection over all R prime in script R of the relation R prime. So then what do we have? So first of all, R star is an equivalence relation. Secondly, R star is also a superset of R that satisfies our requirement. And thirdly, for every R prime superset of R which is an equivalence relation, which is an equivalence relation, what do we have? We have R star is a subset of R prime. Right, so this R star is really what we are looking for, right? And then this R star, right? So yeah, so what should we call it? Yeah, so I don't want to call it transitive closure because transitive closure is something slightly different, which we'll let's just not call it anything. Yeah, but anyway, the point is this R star that we have defined over here is really the smallest. I mean, the point is, given any relation on any set, there exists a unique smallest equivalence relation, which is a superset of the given relation. That's the point that I'm trying to make. Ramanuj?
Yes, sir. So for this, like if we look at a relation as a directed graph, then can we say that if you divide it into disjoint sets, disjoint graphs, then and you complete all of those graphs, then that will be R star?
Yes. You're right. You're right. By the way, I should have mentioned this, right? So if you get back to this, so in so what are the equivalence classes of this relation number 4 over here? We have given some name to them, right? Right, so we called them so basically the equivalence classes of this relation, the fourth relation over here, are nothing but the vertex sets of the partition associated with this equivalence relation is just the partition of the vertex set into kind of vertex sets of the connected components. That's all. Cool. Okay, so yeah, that's all for today. Time is up. See you on Thursday. I'm going to add several problems to the tutorial, hopefully today. All right, chalo then. See you. Bye bye.